All right, so this is our last video, short video on vectors, and now what I want to do is combine what we learned in the first two lessons. We now know how to combine vectors. We talked about combining vectors when they're parallel. We talked about how to combine vectors when they're anti-parallel, that is pointing opposite one another, and then we've looked at what you do when they're perpendicular. But now I want to take a look at a fourth case, and we're going to use vector components to look at how do you combine vectors when they are at angles with one another that aren't 90 degrees. So angles that are not 90 degrees. If it's 90 degrees, it's perpendicular. But what if it's not 90 degrees? What do you do then? If that doesn't make sense to you, if you don't understand what I'm saying, I think it'll be clear in a minute. So for instance, let's again think about displacement vectors, since those are the simplest. And I'm going to imagine a map, maybe. So this is sort of like, imagine that this is a map. All right, and we'll put a little compass up here so we know that, like, this is north, this is south, this is east, and this is west. I'm assuming you're kind of familiar with the cardinal directions on a map like that. And let's imagine that you're moving along the map, and the way you move here is you start, here's your starting point, that's your initial point, and let's say that you go north, straight north, and you go 2 miles. And then I'm going to have you turn and go 3 miles, or we want to go 4 miles, at an angle right here. I'm going to say that this angle right here, theta, is 60 degrees. So we might say that this angle is 60 degrees east of north. East of north. Don't get too tripped up by the language. That just means east of north just means 60 degrees east from your starting direction, which your starting direction was north. So then you end up over here. Here's your final. That's your final point. And we might want to know, what is the resultant? In other words, what would be the magnitude and direction of the straight line path here? What would that vector arrow, what would its length be? And what would its direction be? And so you might wonder, okay, how are we going to do this? Well, this angle right here, this angle is not 90 degrees. So I cannot use the Pythagorean theorem. This angle here is not 90 degrees. You could figure out exactly what it has to be. It has to be 120 degrees, which is not 90. And that means that we can't use the Pythagorean theorem. So how are we going to combine these? So what I'm going to do is try to clarify the picture maybe a little bit. I'm going to erase some stuff just to try to make this a little bit clearer. So we've got our two vectors. Okay. We've got our 2 miles and our 4 miles. And I'm just going to remember that this angle right here we said was 60 degrees. So how do I figure out the length and direction of that green arrow? Well, what I'm going to do, the way I'm going to start, and you might not realize why yet, but it'll become clear to you later. I'm going to start by taking the 4 and splitting it into components. And the reason I'm going to do that is that the 4 is neither entirely in the north, south, east, or west direction. There's a part of the 4 that's north, and there's also a part of the 4 that's east. And so I'm going to start by trying to figure out, okay, how much of the 4 is north and how much of the 4 is east. And so I'm going to use the 60-degree angle to do that. I'm going to say that the north component, north, I'll call n for north, is going to equal 4 times the cosine of 60 degrees, which is 2 miles. And I'm going to say the east, I'm using E for east, and I'm going to use the sine for that. I'm going to say that this equals 4 sine 60 degrees, which is, I don't know, something like 3.6-ish again. And so now I've got the components of 2, and I'll call it 3.6. And you might wonder why I've done that. What has that given me? What's the advantage of doing that? And the reason that there's an advantage is now, since I've split the 4 into components, I can go ahead and I can eliminate this arrow, the blue arrow, because now I've got its components, and the components are equal to the vector itself. So I can just go ahead and get rid of that, and now you might be able to see that, lo and behold, I've got a big right triangle. And the thing I'm trying to figure out, the resultant, R, is the hypotenuse of that right triangle. I hope that makes sense. So what I'm going to do, just to simplify matters, is I'm going to redraw this diagram. Maybe I'll redraw it down here. What I've essentially got here is I've got a diagram with one vector arrow pointed up, which is 2 plus 2, or 4. And I've got another vector arrow pointed to the right, which is 3.6. And now we know what to do. We know how to combine these. I go ahead and I define the resultant. That's going to be equal to the square root of 4 squared plus 3.6 squared. And to find this angle, right, our angle theta, that's our angle theta that we want to find. That's this angle down here. I'm going to say that theta is equal to the inverse tangent of 3.6 over 4. And again, you can use your calculator to figure out these values. But this is a way now of combining vectors or adding vectors when they are neither parallel nor anti-parallel nor perpendicular, when they're angles that are not 90 degrees, using, again, vector resolution, using components. If I wanted to use words to indicate this direction, whatever that degree is, this would be some degree east of north. Some of you may wonder this occasionally. There is an equivalent way of thinking about this, which I didn't do, but which would have been equivalent, is you could get the same thing by putting the 3.6 down here, right? The east down here, and by putting the 4, the 2 plus 2, over here, right? And then you'd have the exact same picture. That is just to say that walking 4 miles north and then walking 3.6 miles east is the exact same thing as walking 3.6 miles east and then walking 4 miles north. I just want to point that out. Right? That's all we have for vectors.